Alright, so the next applications are using the rules of derivatives, defined the rate of change of the function f of x with respect to x at a given c value in the application. So to understand it in terms of the application. Alright, so this is an economy example. Alright, an economist has determined that a certain country's gross domestic products, that would be kind of the value of their economy, GDP, is approximated by that function f of x, where f of x is measured in billions of dollars, and x is the capital outlay. So capital would be your buildings, your infrastructure. So it's how much money you're willing to spend on, your buildings and things like that in terms of merchandise for your economy. All right, so it's the output for the merchandise in billions. All right, how much they're going to spend on capital in billions. All right, so the first question. So you got to make sure you remember that when you go to write your units. All right, what is the gross domestic product, the GDP, when they spend 30 billion on capital? All right, so that's just asking you to take your function, plug 30 into it. Now, make sure you're careful. It's 394 times 30 raised to the 2/5. So make sure, I'll write it that way. Make sure when you take your exponent, my rule of thumb is to always put parentheses around it. So make sure it raises it to the fractional power 2/5. Alright, then that number, when I type that out, comes out 1535.836. Remember, that's in billions of dollars. And so another way you can say that is the GDP is either 1,533 billion or 1.536 trillion. Right. Either way would be fine. It just, again, if the book wants it in billions, make sure you leave it at billions. Or if you change it to trillions, that was what it would be. That's what I would prefer because it's easier to write trillions that way. Alright, next example, or no, same question. Part B. Find the derivative of the gross domestic product at 30 and then interpret what it means with the codependence. Alright, so the derivative first. So this is just a power function. So it's 394 is the constant that comes along. The derivative of the power part, pull my 2/5 out. X raised to the 2/5 minus 1 is going to leave me with negative 3/5. Right, I will simplify that. So 2/5 times 394 comes out to 157.6. X raised to the negative 3/5. Alright, so there's my derivative. And then we want it at 30. So when they spend $30 on capital, $30 billion, the difference between 30 and 30 billion. Alright, comes out to be 20.48. Remember, it's a change in gross domestic product per billion. Everything's in billions, per billion in capital. Alright, so when they spend, this is the interpret part, 30 billion on capital, the GDP will be increasing because it's positive. We know what it is. It's 1.5 trillion, but how fast is it growing? That's the second part. So it's currently at $1.5 trillion, and then this is how fast it's growing. All right, increasing at a rate of $20.48 billion per unit of X. The units on X are billions of capital. Per 1 billion spent on capital. Right? That's what's causing the rate of increase, right? Every $1 billion I spend on capital at that moment, my gross domestic product is going to raise by a rate of 20.48 billion. So it's a pretty good increase, right? It's probably something they want to think about doing if they have the money lying around. Alright, next example. This is a velocity example. So a water balloon has been installed in a treehouse 30 feet above the ground. The equation h of t, which is that quadratic, is the vertical height of the ball in feet above the ground t seconds after it has been launched. Right, find the derivative of the height equation, which gives the velocity of the balloon t seconds after it was launched in feet per second. Alright, so the derivative, negative 32t, right? I pull my 2 out, multiply by the negative 16. That's the negative 32t. The derivative of the 40 is just, or 40t is 40, and the 30 zeroes out. Alright, so that's my velocity in feet per second, right? Because it's the rate of change in height per second it's been launched. So change in feet, which is the height above, in seconds. Alright, so there's my velocity. How high vertically above the ground was the balloon 2 seconds after it was launched? So this is just asking you to use h of t. This is going back to the original, so I'm going back up here. And plug 2 in. So negative 16 times 2 squared, 40 times 2 plus 30, and just make sure, careful when you plug that in. Comes out 46, so it's 46 feet above the ground at 2 seconds. Right, next problem. Use the derivative to find the velocity of the balloon at 1 second, 2 seconds after it was launched. Is it moving up or down at those times? Is the balloon moving faster at 1 second or 2? Alright, so I want to find the velocity at 1 second, the velocity at 2 seconds using the derivative, which I have up here. I'm going to write down here so that we have it. Remember, it's in feet per second. Positive number will mean it's moving up. Negative number means it's moving down. Alright, so at 1 second, my derivative at 1 comes out, if I plug negative 32t, so 8 feet per second is the velocity. And it's moving upward. Alright, because it's a positive. Positive velocity means it's moving up. So it's still moving away from the ground at that time. Still going higher and higher and higher in the air when it's been launched. Alright, after 2 seconds, so again I'm plugging them into my derivative. I get negative this time, right? Negative 24 feet per second is the velocity, and now it's moving downwards. Read that. Because it's a negative. And so the positive and negative is the direction, the number is the speed. So after 2 seconds, the pull of gravity has made the balloon turn around and come down, and it's coming down a lot faster at 2 seconds. At 2 seconds, it's reached a velocity of 24 feet per second, so it's much faster at 2 seconds. And that was the second part of the question, right? Moving faster at 1 second or 2, it was moving faster at 2, much faster, right? 8 feet per second after 1, and 24 feet per second after 2. Right, the next example. The number of ISU students, n of x, right, so that's the function, n of x, who are willing to take the bus ride to Peoria, where x is the price of the ticket in dollars, given by the formula below. Alright, so n of x represents number of students, x represents the price of a ticket in dollars. Alright, find the rate of change in the number of ISU students willing to take the bus ride to Peoria with respect to x, the price of the ticket in dollars. Alright, so I just want the derivative. That's just a fancy way for asking for the derivative. Alright, this is just asking you to find h prime of x. I'm going to rewrite this before I find it. So 6,000, move the x up, that becomes negative 1. 8,000, move the x up, that becomes x to the negative 2. Now I'm ready to find my derivative. Oops, I don't know why I used h. I used h because that was the last problem. N of prime of x is what I'm looking for. Change in number of students per ticket price. Alright, so the 1,500 will zero out. Use my power rule, so that's going to become a positive 6,000. X raised to the negative 2, that's going to become a negative 16,000. X raised to the and so there's the derivative. Right, there's the rate of change function. There's the rate of change in the number of ISU students willing to take the bus ride to Peoria with respect to x, where x, again, that's just saying x is the price of the ticket, with respect to the price of the ticket. How many ISU students are willing to take the bus ride to Peoria if the price is set for $20 per ticket? Alright, so it's just taking how many, so that's not asking for a rate of change, that's just asking you to plug it in the original. How many students are willing? Number of students, that's what the original is. So this is just asking you for n of 20. So 1,500 minus 6,000 divided by 20 plus 8,000 divided by 20 squared. Carefully type that out. so if the price of the ticket is set to $20, 1,800. It's expected that 1,820 students are willing to take the bus to Peoria. All right. Now there's the rates. All right, so that's the difference. This just asked for how many. This asked for at what rate. All right, how many is just the original problem. The rate is finally the derivative. All right, so at the rate, that means I want the derivative. Is the number of ISU students who are willing to take the bus ride changing when the price is set at $1? So again, I want the derivative at x equals 20. All right, so I'm going to plug 20 into that derivative equation. So I'm going to go back and look at my derivative. So that was 6,000, 20 raised to the negative 2 minus 16,000, 20 raised to the negative 3. And again, make sure you're careful with the negatives. Put parentheses around these when you're typing them into the calculator. It comes out to be 13 students per dollar in the ticket price. Alright, so 13 students per dollar is the rate of growth. I believe this is the last question. Alright, after a series of conservative measures to save an endangered species of whales from extinction are to be implemented for the next decade, for the next 10 years. After implementing these, whatever these are to save the whales, the whale population is estimated given that population equation, which is that quadratic, cubic function. PT denotes the number of whales at the end of T years. The domain, since it's over the decade, so the domain is just 0 to 10. So the first question is, what's the estimated number of whales 5 years after they implement the conservative measures? Find the rate of change function, and then at 5 years. So A is just asking you to find the population at 5. So take 5, plug it into that equation. And so when you do that, you get 850 whales. So again, this is a very endangered species. Not a lot of these whales. All right, part B, the derivative. Right, find the rate of change in the number of whales with respect to T, the years after they implemented the measures. All right, so it's just asking you for the derivative. Power rules, so 6t squared plus 12t minus 30, and so there's my derivative. And then C is then asking you to use derivative. Find the derivative at 5 years. So 5 years after they've implemented these life-saving measures, is the whale population growing? And by how much? That's what they want to know. All right, what is it in 5 years? Okay, so if our derivative, plug 5 into it. And then explain what it means. What significant fact does it tell you? Alright, so the number that comes out is 180 when I plug it in. And so that tells me the whale population. Now, after 5 years, there's 850 whales. The derivative is telling me after 5 years, this is how fast the population's growing. Alright, so the whale population is growing, right, increasing at a rate of 180 whales per year, right, per year, that's important, make sure you don't forget the per year, 5 years after they start the conservative measures, I think is how it's worded. Alright, so in 5 years, there's 850 whales, and the population's growing by 850 whales per year. That's how fast new whales are. So the conservative measures are working. Alright, the whale population is no longer in decline, it's now growing. It's only 850, but it's working because the population's getting bigger. Alright, we'll stop there, and then we'll pick up more derivative techniques in the next section.